Thank you all for being here today. It's also great for me to be here today because it's a very familiar place for me. I'm now working at Stedin, but I have worked here for more than 5 years, so I'm really happy to be here today and to see all the improvements that the lab has been made in the past few months. So my name is Tim Slangen. I'm currently working as a Grid Strategist at Stedin, working on power quality and network protection with the Department of Asset Management. As I told, I did my PhD research on power quality at ElaadNL in cooperation with the Eindhoven University of Technology. And I learned a lot about power quality, the effects of new devices, of the energy transition on these phenomena. And I will tell a bit more about that today. Yeah, we saw it in the previous slide as well. If you're interested in reading my thesis, I've included the link in the presentation, and feel free to contact me with any questions you have about this. So a bit about Stedin. Stedin is a grid operator in the provinces of Zuid-Holland, Utrecht and Zeeland, and also some other small areas in the northern part of the Netherlands, just for the gas networks. Responsible for operation, maintaining and management of the electricity and gas networks. We contact about 2.3 million households to the network. The area we are controlling is a quite dense and complex area. We have 3 of the 4 largest cities of the Netherlands, Rotterdam, The Hague, Utrecht, and a very large industrial area around the port of Rotterdam. So it's an area with a lot of energy demand, a lot of complexity, and also a lot of challenges. Some numbers about the company, always interesting to show. So about 2.3 million households connected. Above that, a lot of industrial, very large customers. Last year, we transported about 24,000 gigawatt hours of electricity, and the average interruption duration index is always very low in the Netherlands, and also in the Stedin network. For the whole year, the average interruption was about 20 minutes for the electricity grid, and about 45 seconds for gas. So that brings the uptime of the network to 99.996% for electricity and 99.9999% for gas. So that's beyond the world's best standards that we have here in the Netherlands. Also explains why that many data centers want to be in our country, because the grid is so reliable. So in the Netherlands, we have the 3 largest DSOs, Stedin, Liander and Enexis, controlling the electricity network. Everything below 150 kilovolt and 150 kilovolt, or 110 I should say, and above is controlled by TenneT, the TSO. At Stedin, we have divided our network in different voltage levels. It's a bit of a mess because we have a lot of voltage levels. That has some historical reasons, and also because of we merged from different grid operators into a larger company. That's why we have all the different levels at the moment. But primarily, we use everything above 25 kilovolt for transport over large areas. That's what we call high voltage. Between 10 to 25 kV for medium voltage for distribution of energy, and then going down to 400 volts to the low voltage customers, all the way at the bottom. So my presentation, I divided it in 3 parts. I will first give a brief introduction on power quality. Might be a new topic for some of you, or might need some refreshment. Then I will talk about the new technologies that we see in the network nowadays, and also about the challenges that they bring with them. So power quality, that's a term that's often used, like, oh, we have good power quality, bad power quality, but actually a lot of phenomena covered into it. And this figure is not complete, so some are still missing. But it is about harmonics, imbalance, flicker, voltage level, all these kind of things, which is also regulated in a standardization framework for the grid operators, but also for manufacturers of equipment, to make sure that the electricity network is always working with all components that are connected to it, and vice versa, that the components are not disturbing the electricity network. Power quality is a lot about responsibilities. So this is in fact threefold. You have the customers, the grid operator, and the manufacturers of devices. Well, the customers are all the way at the top. That's the best position to be in, because you're not responsible for anything, and you can complain about everything. So that's really the best position to be as customer. The grid operator is then responsible for what is offered to your connection, so mainly the voltage. And the device manufacturers are responsible for what they take from the network or inject into the network, because this affects the voltage as well. So there's a whole set of regulations talking about what the manufacturers can, or the device equipment should be compliant with, and for the grid operator to also ensure that all customers have a good voltage supply. It's also about compatibility, because the electricity network is a very large system. There are a lot of components connected to it, and this all should work together in a good way. So a figure that is often used is this one. It has multiple aspects. On the bottom left, let me see if this works. Yes. There's, for instance, the emission limits of individual devices. So this is a quite low limit, because in the end, this emission might result in a higher level for the whole system. Then the levels at which systems should be immune, or components should be immune, is always higher than the emission limit. So that's over here. And what is in between is what we call the compatibility level. And as you see, there's a bit of an overlap between the largest possible emission of a system and the lowest immunity of equipment. And this means in practice that indeed the worst 5% of equipment will not perform well in the worst 5% of the grids, but that's something we accept. Because in order to separate the curves completely, that would be economically unfeasible. That would cost a lot of money. So that's why we put the compatibility level at about an overlap of 5%, so that 95% of the equipment works well in 95% of the environments. That's where this level is set to. Now, power quality, the word power is of course a combination of voltage and current. And then if you take the ratio of voltage to current, you get impedance. So power quality is about voltage, current, and impedance. So, that's Ohm's law. That's not that fascinating, I would say. But it is very interesting to understand this basic concept. Because on the one hand, the network impedance and the voltage, that's where the grid operator is responsible for. And on this side is the manufacturers of equipment. They put load to the network that draws certain current. And in the end, this current, in combination with the impedance, will disturb the voltage. So power quality is always about voltage and current and the interaction between both. And this is really important because when measuring or monitoring power quality, it's often only about the voltage. And of course, that's the real impact on the network. But it's also important to look at the current as well, to understand why things are happening in such a way, and to see the whole picture. We are, of course, in a transition. The energy transition is ongoing. And this means in order to reduce our overall energy consumption, we need to increase our electricity consumption. And it might sound a bit strange, but in order to make more use of renewable energy and more efficient use, one way to do that is to, for instance, heat your house not by gas, but by using a heat pump. So we need to use more electricity to reduce our total energy consumption. And one way to do that is to change the way we use energy in our network with new devices. And those new devices are often based on converters. So the traditional networks we have, they work on an AC voltage, alternating current. Voltage, if you translate it, is a bit strange. That's also what the network offers to the customers. But most devices work actually on a DC voltage, so direct current voltage. This means that in order to use your electric vehicle or your heat pump or to connect your PV installation to the network, you need to convert this AC to a DC or vice versa. And in order to do this, you need a converter. And you can find the converters in all kind of devices that you have in your house nowadays. The charger for your phone, for your laptops, LED lights, but also the larger devices like we just talked about. The thing with these converters is that they make sure that we can use renewable energy, but they also put some challenges on the network. They can namely cause disturbances in voltage and current. Now, how does that work? I will explain. So ideally, the waveform of the network, voltage or current, is a sinusoidal waveform, like in the left part of the figure. But when a device is connected to it, it might inject an additional distortion component on top of this ideal waveform, which means that the resulting waveform will then look like in the right figure. Now, this is okay, as far as it is within the limits. But nowadays, with the increasing share of converters, we see these distortion levels also increasing in the network. In the past, distortions were mainly low frequency, so that's what we call harmonics. So that's an example in the top figure. These are disturbances with a frequency below 2 kilohertz that are at the fundamental multiple of the fundamental, so it's quite easy to measure and to look into it. It's also really well covered in standardization because that's been known for several decades, harmonics. So that issue is quite under control, I would say. But nowadays, with the increasing numbers of large converters who make use of switching frequencies above this harmonic range because that's more efficient and cheap to build, there's also an increase in supraharmonic emission levels. Supraharmonics are at higher frequencies than the harmonics, so that's everything above 2 kilohertz. They are totally unrelated to the fundamental, so the name harmonic would imply it's a multiple of it. It is not. And the research is only there for about 10, 20 years, so it's a really new topic, and there are no limits on it yet. And this is where the main challenge lies at this moment with all these new converters in the network and the disturbances they bring. Now, this was also the topic of my PhD research, so I will dive a bit deeper into this phenomena. So the sources of supraharmonics, it's not that new because we know all these small devices already moved in the past years to larger electronic devices that you find in your house, so the PV inverters, the charger for your electric vehicle, heat pumps. But in the future, and not even future, also nowadays, is increasing to larger installations like the large fields with PV plants, the large fast charging stations. So these type of devices are growing not only in size, also in power, and by that also the disturbances will increase in the network. Now, here's a whole list of things supraharmonics can cause, interference and impact, but I always think a picture tells more than 1,000 words, so I will show some examples. Because of this lack in standardization, components or equipment are not really immune to supraharmonics. So things that can occur are, for instance, the failing of protection systems, heating of equipment, failure of it, audible noise from induction cooking plates, other equipment, failing of cable terminations, coffee machines that only make tea. So it's a whole bunch of quite specific problems that occur, mainly due to a lack of standardization. And a lack of standardization, there is something. This is a list. I will not go through it all the way, but the domain 2 to 150 kilohertz, there is something written down in standardization, but unfortunately the list of missing standards is at least as long. So these are issues that people are still working at, and where there is a need for standardization in order to solve these problems. So we talked about broadly power quality, the new technologies we see in the network, and a bit about the challenges. But I will now dive a bit further in the challenges that I found during my PhD research here at the ELAAD test lab that are related to electric vehicle chargers, but also apply to all different kinds of larger inverters. It's again threefold. I will talk a bit about primary and secondary emission, about factors that influence emission of a device, and about impedance, and that is what Thijs also was talking about. I said it's right, impedance, it should be impedance, I think. Primary and secondary emission, this is a very important distinction that you should make if you are going to do research on a power system, on equipment. Because if you're just going to measure a device that's connected in a network and say, oh, this is the emission from this device, wrong, it is not. What you measure is always a combination of the device, the network, and all other equipment that is connected in it, what you're not capable of controlling. So the definition of primary emission is the emission that a device has when it is connected to a clean network when nothing else is connected. That's what we call the primary emission. Now, in practice, there will be also a grid connected to it, and this primary emission will also might be affected by other devices that are connected to the network. So in this example, we have one device with a certain emission, this is I supraharmonic 1, a certain impedance, so this is the simple Norton representation of the device, the network, and another device that is in this case just an impedance. If you then look at the primary emission of device 1, which you measure at this point, this is not anymore just this value. It is the division of the current through the different impedances of the device itself, the grid, and the secondary device. And in this case, it's still quite simple. But that second device, if you're going to measure at that point, you will also see a part of the emission from device 1. So this emission will start here, flow through the internal resistance of the device, to the network, but also to the secondary device, which means if I'm going to measure at this point of device 2, I will see the emission of device 1. And you can't distinguish between both. And to make it even more complex, if now device 2 is also a source of some disturbances, if you're now going to measure here, you will always see the combination of this part and that part, the whole equation. And this is an equation with more unknowns than number of equations, so it's impossible to solve mathematically. And this is why it is so important to test equipment on networks without additional devices, so not just in the grid, but make sure you have a network you know, with a clean voltage source, for instance, and do your test there. And that's a way to cope with the difference between primary and secondary emission. Now, it's also something that I saw in practice. So this is a figure where the emission of two electric vehicle chargers is plotted with respect to each other. So this is the emission of device 1 and the emission of device 2. And it looks quite strange. Where are we looking at? This is the combination I was just talking about. So if just device 1 is active, you see this emission. It's just emission from device 1. If just device 2 is active, we see just the emission of device 2. But if we activate them both, we see something else happening. And there's a whole wide spread of possible emission values that might be caused by device 1 or device 2. It's not a linear combination. You can't add them and get the result. So there's something else, some interaction happening there. And this is a challenge we are dealing with in practice, because if you put multiple identical devices next to each other, this is what will happen. And you can't tell beforehand what this emission will be. So that's something you need to test. Now, we talked about emission, how emission from two devices can interact and cause any kind of strange phenomena. But this emission from a device is also not always constant. So to make the total picture even more complex, we're going to add more variables to the equations. If we have a device, for instance, an electric vehicle charger. Now you have them all over here, of course. And we connect them here to the network, and we measure what the emission will be. We get the result. So, we know what the emission is. Let's put it in the field. Everything is within the limits. But if we then put the charger in the field, the emission you get from the charger might be totally different. And this has to do with the fact that the emission is also dependent on what you put into it as a voltage. So in this example, we have this is what we call a complex diagram of an harmonic voltage in this case. A harmonic might occur at a certain amplitude, so a few amounts of a volt, and a certain phase angle. So anything between in phase to the fundamental to totally out of phase, and any random value in between. So using a source that can inject harmonics at different amplitudes and different angles, you can get an idea of how the device will react in certain grid environments. So that's what we did in the research. And what was seen, that this emission that we first thought was constant, at this point is not constant anymore. So dependent on the angle of the harmonic that is injected and also the amplitude, the emission changes between 3 and 4 amps. And so this means that dependent on what is there in the background voltage, harmonics, also changes the emission of the device that is connected to it. And not only at the voltages we inject, but also at other disturbance components that are there for this device. So this is looking at one side. So in the case of the charger, we have the charger connected to the network. The network is an AC source where something can change. But this charger is on the other side connected to a vehicle, a battery. And this battery is not always at the same state of charge. It might be different vehicles. So what the charger will see at the DC side of it will also change depending on the type of vehicle connected, the state of charge, all these kind of different things. And this is also something interesting to look at. So in this part of the research, looks at the operating conditions. So I made a whole graph of for a charger that is capable of doing all the way from 500 volt to 800 volt over different output currents. You can make a whole table of different operating conditions where the charger will or can work at. And if you then test the charger for the different operating conditions, you will as well find that depending on what is there on the DC output, so the type of vehicle, state of charge of the battery, that the emission on the AC side will also change. So this means that there are different factors that contribute to the emission of a device where you have no control over in practice. So this means that it is very important to test all the different kind of devices for not only different grid conditions, but also for different operating conditions. Now, sometimes the results look very linear. So in this case, it's a quite linear plot, which is really easy to model. But that's not always the case. So in this example, I used a linear model to describe the emission of the charger depending on the DC output power and voltage. Quite easy model. But in practice, I'm sure with all these charges that are over here, I'm not sure if that will always be such a linear relation. So that's also why it is so important to test. Now, another small example, I will briefly go over this because Thijs already told about it in the previous presentation, the supraharmonic impedance. So this is again the same figure as we saw before, but now I added the frequency-dependent part to it, because this network, of course, has an impedance at 50 Hertz at the fundamental frequency. But if we are looking at disturbances, we also should be able to, or should know what the impedance is for these higher frequencies. So, traditionally, looking at cables and transformers, this impedance is quite straightforward. You have an extrapolation of the fundamental impedance over frequency, so that will just increase with frequency. But with all the devices that we connect, it's not linear anymore. So it's more of a capacitor behavior, and impedance might more look like something like this. Which means that the total impedance of the network will be a combination of both, depending on where you measure, on what kind of devices are connected, making it very difficult to determine what, for instance, this current should be at maximum, because the maximum current depends on the impedance. Now, some conclusions and solutions. I was looking at some pictures from Stedin, and I found this one. I found it very, very nice. A few years ago, they rolled out new smart meters at Stedin and also at the other grid operators. I was not working at Stedin at that time, so I'm not sure about the details. But I found this picture of a guy with an electric cargo bike installing the meters at different houses. And I'm not sure if they did the whole region of Stedin with this electric bike, but at least the palace from the royal family, the Paleis Noordeinde, got their smart meter installed by this electric cargo bike. And I thought it was a very nice solution to sustaining the renewable image of a company by using electric bikes instead of fossil vehicles. Now, talking about real solutions for the problems we were looking at in this presentation, I think it is really important to test high-power converters, like electric vehicle chargers, for different grid conditions and different operating conditions. It is very important to include also effects of the impedance of the network and of devices, especially for the supraharmonic range, to get more insight on what is there in the field. Grid operators should measure and monitor at different voltage levels what is there. And I think the last one, maybe the most important one, is cooperation between grid operators, manufacturers, and standardization bodies in order to achieve an overall understanding of the different challenges that we face and to be able to work on this together. In conclusion, we are in a transition to our converter-based system. So in order to make more use of renewable energy, we need to increase our use of converter-based devices. Like all new technologies, this will also bring new challenges. It brings a lot of positive things for the network, for the whole society, for the environment, but also new challenges. And in order to cope with it, we need to research and test to make sure what is going on. And I would like to say congratulations to ELAAD on this topic, because with achieving this new testing system, that's a great step forward in this testing and measurement and to better understanding the different challenges we are working on. Because in the end, I believe that if we cooperate and if there will be standards describing the challenges we are facing, ahead lies a sustainable and a future for everyone. So, thank you.